Welcome to the chemistry studio. Today we will start chemical kinetics. Rate of the reaction. It is defined as the change in concentration of reactants or products with change in time. Rate is equal to change in concentration upon change in time. R is equal to change delta, concentration C upon change in time. Unit is mole per liter per second. Let A forms B. A is reactant, B is product, and with the passage of time, suppose initial concentration of A is 100 gram, 100 mole, whatever. Initial concentration of B is 0. With the passage of time, the concentration of A will decrease. Suppose 20 gram of A is left and 80 gram of B is produced. Now, rate of disappearance of A is disappearing with respect to time. That must be change in concentration of A upon change in time. And rate of appearance of B, it must be change in concentration of B upon change in time. But this is initial concentration of A and this is final concentration of A, and the change in concentration of A will be final minus initial. That will be 20 minus 100 and will come out to be negative. But the rate can never be negative. Therefore, we put a unit negative sign before the expression of the rate of the reactant. This negative sign, as we know, the initial concentration of reactant is more than its final concentration. Therefore, rate will come out to be negative. Rate will come out to be negative. But rate can never be negative. Therefore, we put a unit negative sign before the expression of rate of reactant. रेट ऑफ रिएक्टेंट से पहले हम नेगेटिव साइन लगा देंगे। तो ये जो नेगेटिव साइन है ये इंडिकेट कर रहा है देयर इज अ डिक्रीज इन कंसंट्रेशन। नेगेटिव साइन indicates decrease in concentration. Decrease in concentration. Now let us consider a reaction in which 2NH3 forms N2 plus H2. Let initial concentration of N2 is N2 initial at time t1 and final concentration of N2 is N2 final at T2. Therefore, change in concentration of N2 will be N2 final minus N2 initial, and change in time will be equal to T2 minus T1. Now the rate in terms of nitrogen will be change in concentration of nitrogen upon change in time, and the rate in terms of hydrogen must be change in concentration of hydrogen upon change in time, and rate in terms of ammonia must be minus change in concentration of NH3 upon change in time. Now all these rates, this is the rate of formation of 1 mole of nitrogen, this is the rate of formation of 3 mole of hydrogen, and this is the rate of decomposition of 2 moles of ammonia. In order to equate them, rate of nitrogen is equal to 1 by 3. We must divide them with their stoichiometric coefficient is equal to minus 1 by 2 change in concentration of ammonia upon change in time. Now, in case of reactant, if we plot a graph for the average rate, x, y, this is concentration and this is time. At t is equal to 0, there must be some initial concentration of the reactant which goes on decreasing with respect to time, and it becomes parallel to x-axis. We do not consider the reactant concentration to be 0. This is time t1. At t1 the concentration is c1. This is t2. At time t2 the concentration is c2. Now the average rate will be equal to c2 minus c1 upon t2 minus t1. Again c2 is less than c1, therefore it will come out to be negative. Therefore we put a unit negative sign, and this is change in concentration of the reactant upon change in time. This is the average rate. Now in case of product, for product, x-axis, y-axis, this is concentration, time. At t is equal to 0, the concentration of product is 0, which goes on increasing and then becomes constant after some time. This time is t1, concentration is c1, this is t2, concentration is C2. Therefore, average rate will come out to be C2 minus C1 upon T2 minus T1 delta C over delta T. This is average rate. Now, instantaneous rate. The rate of the reaction measured at any given point of time. At any given point of time. For instantaneous rate of the reactant X, Y, concentration, time. At this point T, at this point we draw a tangent and complete the triangle. Now instantaneous rate is equal to limit delta T approaches to 0 for the time change is 0, change in concentration upon change in time. This is minus dC over dt. This is also known as differential rate. This is very small change in concentration and very small change in time. Now for the product, concentration, time, the graph will remain the same. At this point T, draw a tangent, calculate the slope. R instantaneous will be equal to limit delta T approaches to 0 delta C over delta T is equal to dC over dt. This is the differential rate for product. Now next topic is rate law. It states that the rate of a reaction is directly proportional to the concentration of reactant raised to the power of some integer whose value may or may not be equal to its stoichiometric coefficient. For example, let n moles of A form product. Then rate will be proportional to concentration of A. Power may be equal to n or may not be equal to n. We are taking it is equal to n. We'll consider the case later when it is not equal to n. R is equal to some constant K, A power n. K is called rate constant. And this power is called order of the reaction. Order of reaction. Let us consider a reaction in general terms: X moles of A plus Y moles of B react together to form product. Then the rate is equal to some constant concentration A power X, concentration of B power Y. Then value of N will be X plus Y. This is order of the reaction. Now if we define the order of the reaction, the order of the reaction is defined as the sum of all the exponents raised to the power of concentration in rate law expression. In rate law expression. Order is measured experimentally. Order can be 0, 1, 2, 3, 4 and fraction. We will be taking the example. Order must not be measured from a balanced chemical reaction. Balanced chemical reaction. Order can be measured for elementary. Elementary means taking in one step, and complex reaction. Complex, which is taking in more than one step. Complex reaction. Now let us take example of zero order reaction. Zero order reaction. This is catalyst. These are the reactant particles. Now we know that the reactant particles are always in their random motion, therefore the probability of collision is very less. But when they are trapped on the surface of the catalyst, the collision can take place very easily. So most of the reaction takes place on the surface of the catalyst only. Now we know that in the first step, suppose there are four reactant particles. Four reactant particles in the first step, they collide and the product is formed. The product formed, suppose this is the product. Now all these vacant sites are again occupied by these four reactant particles. In the second step, again there are four particles. They collide together, the product is formed. It goes on like this. Each and every time the concentration of the reactant is same in each step, and the rate of formation of product is constant. So this kind of reaction is zero order reaction. In this reaction takes place on the surface of the catalyst. The concentration of reactant does not change with time. That is, the rate is independent of concentration of reactant. For this, R is equal to some constant K, concentration of the reactant power 0. R is equal to K. The rate is constant. As we can see, the rate is constant. Example of the reaction is decomposition of ammonia on the surface of iron in the presence of molybdenum. This is zero order reaction. But if we write the rate of this reaction from the balance equation, it must be like R is equal to K concentration of NH3 power 2. Therefore, order comes out to be 2. But it is zero order reaction. Therefore, we do not write the order, the rate law from the balance chemical equation. Now let us consider the example of fractional order reaction. Reaction of chloroform with Cl2. In the presence of sunlight, it forms CCl4 plus HCl. Now this reaction, if we write the rate law from the balance chemical equation, it must be CHCl3 and Cl2. Order must be 2. But this is fractional order reaction. We must know the steps in which the reaction is taking place. First of all, Cl2 gets split to form free radicals. Now these free radicals, they react with chloroform. It forms CCl3 free radical plus HCl. And this CCl3 free radical reacts with Cl free radical in the presence of sunlight to form CCl4. This reaction takes place in 3 steps. This reaction is taking place in 1, 2, 3, 3 steps. And we have already given that this step is the slowest step. Slowest step is the rate deciding step. Slowest step is the rate deciding step. Now we write the rate from this slowest step is R is equal to K concentration of CHCl3 and concentration of Cl free radical. But we know that Cl free radical is an intermediate. It is an intermediate. Therefore, we must not write this intermediate in the rate law. Cl2 gets split to form 2 Cl free radical. Therefore, half Cl2 will give 1 Cl free radical. We can write half Cl2 instead of Cl free radical. Therefore, the rate will be equal to R is equal to K CHCl3 Cl2 power 1 by 2. And the order comes out to be 1 plus 1 by 2. This is 3 by 2. So this is fractional order reaction. Now unit of K. Let n moles of A form product. The R is equal to some constant K, rate constant, power n. Therefore K will be equal to R upon concentration A power n. Unit of R, we know that it is mole per liter per second, and concentration of A, mole per liter power n. Now if we take n is equal to 0, it means K will be equal to mole per liter per second on mole per liter power 0, and the unit will come out to be mole per liter per second. For 0 order, K has unit mole per liter per second. For n is equal to 1, if we put n is equal to 1, then K will be equal to mole per liter per second mole per liter power 1, and the unit comes out to be per second. This is how we can also calculate for n is equal to 2, 3 and so on. That is all for today. Thank you for watching.